So first, the tests. I don't have them finished yet, um, but let's see. I think I told some people I was halfway through. That was a lie. I'm sorry. uh, but I'm probably a quarter or a third of the way through. And so far the results have been awesome. Like just what I hoped. Like uh, maybe all A's so far that I've graded. So I mean, but I did start with the first people who turn them in. So it's sort of like. Um, so it's a little biased always. But anyways, so far it looks really good overall. And I'll have all the grades posted uh, by tomorrow night, I think. I should be able to. Uh, planning on um, planning on a good nap for my son tomorrow. 'Cause I'm taking care of him tomorrow. So no nap. It might take a little longer. Um, and so, well, anyone have any questions about the test? Okay. Anyone have any venting to do about it, or, I mean, it was, I hope it, and it looks from what I've seen so far like it, it was pretty, like if you did the practice problems and stuff, you were in pretty prepared for it. And um, hey, like if everyone gets A's on this, I mean, I think this is just what you need to be able to do in this class, and I'd happily give out A's to everyone on this. Um, so I mentioned before that the next topic is friction, but I think uh, so. If you look at the textbook, we still have a lot of weeks left and not a lot of chapters left. So I'm going to stretch out for a day or two and just go into a little more detail on how to do internal loads of members of structures when you're including the weight. Okay. And what's hard about that, what's different about that we haven't seen yet, is that you have distributed loads that end up having horizontal and vertical components. Okay, so we've dealt with only vertical components. Now we're going to see how to deal with distributed loads that are full vectors. Um, it's an interesting problem. Obviously, it's very applicable to anything. Like so far, when we've dealt with internal loads of structures, we've had to do it with members uh, whose weight is negligible, which tends to mean really enormous forces, and those aren't always what you're dealing with. Like in any biomechanics calculation or something, you wouldn't be able to neglect the weights and get good results, because the the weights are sort of on the same order of magnitude as the joint forces applied. Um, so, and I mean, it's a cool problem because it's not in any statics books, uh, you know. So when you go to the U or whatever, you can be like, look what I can do. Yeah, right. You'll be the cool kids. And that's all anyone wants in college, is to be the cool kid. Yeah. Um, so I'm gonna present this in the form of an example problem that we did before the exam um, without dealing with the weights, and we're just going to include the weights this time and see what changes. So, oh, thank you. This is more riveting video for later. Okay, so here's the problem. Um, you have a vertical member and a diagonal member. And this is connected with rollers. And then you have a horizontal member sort of holding it all together. A 10,000 Newton force acting up. And you have pin here, pin here, pin here. This is on a pin. And I'll just use the same numbering system I used before, which is a little bit of an odd numbering system, but that's 1, 2, 3. And then for some reason I called this A, B, C, D, and E. And the dimensions you need, this is acting, or positioned at the midpoints of these two members. And this is 1 meter, and this is 1 meter. So that diagonal member is square root of 2 meters. And this time, what's going to be different is we're going to assume the mass, and maybe I'll call it the mass density of each member is 5,000 kilograms per meter. This is sort of, notice it's sort of an unusual kind of density. This is what I was getting at with the way I gave the masses in that problem set that was a little confusing to people. Usually you give density per volume, right? I'm giving it just per length because we're assuming that the cross-sectional area is the same and it's the same material. And we want to calculate the greatest tension, shear force, and bending moment in this whole structure. Okay, so first, work together and calculate the external loads on each of those members. And then we'll break it down into pieces, and you can do the pieces we've done before. I'll show how to incorporate the horizontal members. And oh, yes, 45 degrees. Let's see. Actually, you can get that from knowing these are all at the midpoints. You can, yeah. Yep. Because this is half and this is half, right? Okay, so yeah, go ahead, talk out loud, work on this problem, get the external loads on each member, and by the way, present these external loads. I didn't take off points for doing this on the exam, but the way that I'd like to see these external loads, since we're going from the external loads to calculating the internal loads, is, when you calculate the loads of this structure, you're going to treat all those distributed loads as point forces. But then when you draw out the members with their external loads at the end, draw them back as distributed loads, okay? Because that's what we're going to have to use for the problem when we go into the internal load calculation, okay?